A rocket carrying a decade of human ambition exploded 40 seconds after launch. The year was 1996. Europe had spent the better part of a decade and billions of dollars in development costs, building the most powerful rocket it had ever produced. On its very first flight, it destroyed itself in less than a minute. No external attack, no fuel leak, no mechanical failure. The cause was a single, unprotected line of code, borrowed from a previous rocket, trusted without question, and never tested against the conditions it would actually face. This is the story of the Ariane 5 disaster. But more importantly, it is the story of how a hidden assumption, buried inside a working system, waited patiently for the right moment to become catastrophic. The question Null Theory always asks is not simply what broke. The real question is, what hidden weakness inside the system allowed this to happen? To understand the disaster, you first need to understand what Ariane 5 represented. The Ariane program was Europe's answer to a critical question: could the continent compete independently in the global space race? For nearly 2 decades, the European Space Agency, ESA, and its industrial partners had built a reputation for reliable, commercial launch capability. Ariane 4, its predecessor, had completed 113 successful launches from a total of 116 missions, one of the most reliable launch records in the world at the time. Satellite operators and commercial customers trusted it with billion-dollar payloads. Ariane 5 was designed to go further. It could carry nearly double the payload of its predecessor, opening new commercial opportunities and cementing Europe's position as a serious spacefaring power. The rocket wasn't just technology. It was a symbol of what coordinated European engineering could achieve, and on the 4th of June 1996, the world was watching. Inside Ariane 5's guidance system lived a piece of software that nobody questioned. It had worked perfectly for years. It had earned its trust. The code in question was part of the inertial reference system, the software responsible for calculating the rocket's position and velocity during flight. A specific function within that code converted a 64-bit floating point number into a 16-bit signed integer. That sounds technical. The human consequence was simple. When the number being converted was too large to fit inside a 16-bit value, the software produced an operand overflow error. The inertial reference system was a self-contained unit. It performed its own calculations internally and passed the results outward as navigational data. When it failed, the guidance computer had no way of knowing the output it was receiving was a diagnostic error rather than a real flight reading. It responded exactly as it was designed to. It tried to correct it. The correction tore the rocket apart. But investigators soon realized the disaster wasn't born on launch day. The software had been written for Ariane 4. On that rocket, the horizontal velocity values encountered during flight were never large enough to trigger the overflow. The code worked. It was validated. It was certified. When engineers began designing Ariane 5, they made a decision that seemed entirely reasonable at the time. They would reuse proven, certified software components wherever possible. Why reinvent what already worked? The inertial reference system software was carried across, trusted, unchanged, unquestioned. What nobody fully accounted for was that Ariane 5 flew a fundamentally different trajectory. Its greater thrust and acceleration meant the horizontal velocity values it encountered in the early seconds of flight were significantly larger than anything Ariane 4 had ever seen. The software had never been tested against Ariane 5's actual flight conditions. It had been assumed, not verified, to be compatible. At approximately 37 seconds after launch, the overflow occurred. The backup inertial reference system failed first, for the same reason. Then the primary system failed. Both units were running identical software. An error in one was guaranteed to be an error in both. The guidance computer received corrupted data. It commanded the nozzles to deflect. The rocket veered off its intended flight path at high velocity. Aerodynamic forces broke the solid rocket boosters away from the main stage. The range safety system, detecting that the vehicle had become a hazard, sent the destruct command. Ariane 5, along with 4 scientific satellites it was carrying, was destroyed over the Atlantic Ocean near Kourou, French Guiana. 40 seconds. A decade of work, gone. The inquiry board convened quickly. Its report, published just weeks after the disaster, became one of the most studied documents in the history of software engineering. Investigators identified the overflow. They identified the reused code. They identified the assumption that had never been tested. But the investigation uncovered something even more significant than a single programming error. The report noted that certain variables within the software had been left unprotected, a design decision made based on assumptions about the range of values the software would encounter. Those assumptions had never been re-examined when the software was transferred to a new rocket flying in fundamentally different conditions. Investigators also noted that the specific function causing the failure was not even necessary during flight. It was part of an alignment process used before launch. It continued running in flight because nobody had stopped it, not because it was needed. The uncomfortable truth was that no single engineer made a catastrophic error of judgment. The software developers had written code that worked. The validation team had tested it correctly, against the system it was built for. Project managers had made a rational decision to reuse certified components. The failure lived in the gaps between those decisions. When the software was transferred from one rocket to another, the assumptions it carried were not formally re-examined. There was no systematic process requiring engineers to prove that a component designed for one environment remained valid in a fundamentally different one. A certification that had once meant, "This software is safe," had silently become, "This software was safe, somewhere else, under different conditions, against a different set of demands." That distinction had never been confronted, and nobody had thought to ask. The immediate loss was significant. The 4 cluster scientific satellites, designed to study Earth's magnetosphere, were destroyed, representing hundreds of millions of dollars in scientific investment, wiped out in under a minute. The reputational damage to the Ariane program was serious, though ultimately manageable. European launch capability had to be reasserted through subsequent successful missions. The deeper consequence was institutional. The failure forced an industry-wide reckoning with how software components are validated, how assumptions migrate invisibly when technology is reused, and how a system can pass every test and still fail catastrophically the moment conditions change. The Inquiry Board's report was unusually candid. It identified not a villain, but a process, one that had allowed a reasonable set of individual decisions to combine into an unreasonable outcome. What happened next changed industry thinking in ways that extended far beyond aerospace. Investigators were troubled not by what engineers had done wrong, but by what the process had never required them to do right. Software carried into a new operational environment had never been required to prove it belonged there. Exceptions in safety-critical systems had been permitted to produce outputs that downstream components could not distinguish from valid data. Functions with no flight purpose had been permitted to run during flight simply because nobody had formally decided otherwise. Each of those absences became a requirement. Independent software verification gained new urgency. The principle that those who validate a system should not be the same team who built it. And defensive programming, designing software to handle unexpected inputs rather than assuming they will not occur, moved from good practice to foundational expectation across aerospace, medical technology, and financial systems alike. The Ariane 5 disaster is often reduced to a simple lesson about data types and overflow errors. That reduction misses everything important. The real lesson is about how complex systems inherit the assumptions of the systems that came before them. Assumptions that were once valid. Assumptions that were once tested. Assumptions that nobody thought to question again, because the software had a certificate, and the certificate had always been enough. Every organization working with legacy systems, inherited code, or reused components faces a version of this risk today. The software wasn't broken. The process that carried it into conditions it was never designed for, that was where the system failed. The rocket worked exactly as its guidance computer commanded. The guidance computer responded exactly as its software directed. The software did exactly what it had always done. The only thing that changed was the world around it. That is the hidden danger Null Theory exists to explore. Not the dramatic failures that announce themselves, but the quiet assumptions that accumulate inside systems, until the conditions finally arrive to expose them. Which system in your life do you think is running on assumptions nobody has questioned in years? And which hidden weakness do you think most people are trusting without realizing it? Leave your answer below. Subscribe to Null Theory for more investigations into the hidden failures inside the systems that shape our world.